There are a few situations where you might need to upgrade your smart contract. It can be to fix a security vulnerability, change the business logic, or add new features. But once you deploy a smart contract, its code is immutable. You cannot change it. Fortunately, there are a few tricks to make your smart contract upgradable. Everything I will show you in this video works on any EVM compatible blockchain, which means Ethereum of course, but also Binance Smart Chain and Polygon. If you don't know me, I'm Julien, and on EatTheBlocks I teach blockchain development. The first method to upgrade your smart contract is by using a proxy. When a user interacts with your smart contract, it first goes through a proxy smart contract that forwards the function call to the actual implementation represented on this graph by v1, v2, v3. When the user is going to call a function on the proxy, this function doesn't actually exist on the proxy, but thanks to the fallback feature of Solidity, we are still able to process this call. And inside this special fallback function, we will forward the call to the actual implementation. We will use a special opcode of the EVM called delegatecall that allow you to execute a smart contract in the context of another one. So that means, for example, when we execute the call of v1, if we change any state variable, it will actually change the storage of the proxy smart contract. It will not change the storage of v1. v1 is just for the code. Later, when we want to upgrade our smart contract, the admin is going to deploy the v2. After, the admin is going to update the address of the implementation in the proxy. And the next time the user will make a call through the proxy, this time the proxy will forward the call to v2 and not v1. So I prepared a demo in the GitHub repo of EatTheBlocks. So we will go inside contracts, and here we have two example implementation, v1 and v2. So this is a very simple smart contract that just updates an internal variable, and in v2 we've added another function. So let's go to the proxy smart contract here, and first we will go to the fallback function. So when a user wants to interact with our implementation, it's going to call a function that does not exist on the proxy. So this fallback function is going to be called, and we are going to use assembly to forward our call to the implementation. And that's because for some advanced use case like this one, we cannot use Solidity directly. We have to resort to assembly. So first, we are going to retrieve the address of the implementation. And for this, we use the opcode sload that allow you to load some data from the storage. And we store this in a temporary variable called target. Then we are going to copy paste the function call to memory. So for that, we use a built-in function of assembly called call_data_copy. And we give it first the memory slot where we want to copy it to, and also the memory slot of the call data that we want to copy it from. So we want to start from the beginning. And after, we specify the size of the call data to copy. So we want to copy everything. So here we call another built-in function called call_data_size. And after, we are going to forward the call to our implementation. And for that, we use the delegatecall opcode. And so the first argument is how much gas we forward to this call. So here there is another built-in function of assembly that tells us how much gas is available to us. Then the address of the implementation. Then we need to specify which function we want to call and with which argument. So for that, we are going to read from memory. And remember that just before we copied the call data into memory, we're going to start from the first slot in memory. And again, we're going to use call_data_size to know where the call data ends. And for the last two arguments, I'm not too sure, but I believe this is related to where we want to start in the storage of the proxy, because with delegatecall, we are going to call our implementation smart contract, but any modification of the state will actually be done in our proxy smart contract. And after, we're going to have a Boolean value depending on whether this call succeeded or not. And we're going to store this in result. And after, we're going to use another built-in function, return data copy, in order to copy the return data and return it from the fallback function. So all of this is the equivalent of return in Solidity. Then we're going to use the return data copy function to copy any data that was returned by the previous function call, and we're going to copy this in memory. And after, we're going to use a switch case statement. So it's similar to if statement. So if the result here is equal to 0, it means that the call failed, and so in this case we are going to revert the transaction. Otherwise, we are going to return the data that was returned by our function call, and we're going to read from memory, so from the first slot, and we use another built-in function here, return data size, to know size of the return data. Okay, so that was the hardest part, but we still have a couple of other functions. So there are two things that we need to store in our smart contract. First, the address of the admin and the address of the implementation smart contract. So we could just declare these two variables as state variable at the beginning of our contract. But the problem is that if we do this, when we execute functions in the implementation, and if this function modify the state of our proxy, it's going to overwrite any state variable that we already define at the proxy level. That means we will lose the admin address and lose the implementation. And of course, we don't want to do this. So we are not going to use state variable defined in Solidity, but instead we're going to use assembly. So in a Solidity smart contract, when you store a variable in storage, you can store your variable at arbitrary position. And so here we have defined two arbitrary address, admin slot and implementation slot. And if you wonder why we took this specific number, this is actually part of a standard for proxy called ERC1967, and this is the hash of a specific string. And so here we have our two memory addresses for these two variables. And so in our constructor, when we're going to initialize the admin, so first we copy the admin slot into a bytes32 variable. We also stored the address of MSG sender into a local variable because you cannot access MSG sender in assembly. And after, in an assembly block, we are going to use the SSStore opcode. So this allows you to store a value in a storage of the smart contract. And first you specify the address. So here this is our memory slot, and after this is the value. And after that, we're gonna have a function to return the value of the admin address. So again, we copy the slot of the admin, and in assembly, we use the opcode sload that allow you to read a value from the storage. You pass it the memory slot, and we store this in a temporary variable. And after here, we specify that we return this variable. We also have the same thing for the implementation. And when we want to change the address of the implementation, we have this upgrade function. So we need to pass the address of the new implementation. We verify that the sender is the admin. And so here we make use of the admin function that we created before. Otherwise, anybody can change the implementation, and this is a huge safety concern. And after here, we store in memory the new address of the implementation. Okay, so that's it for the proxy smart contract. And next, I'm going to show you how we can test this. So here in the test folder of my Truffle project, I've created a test file. So first we import the Truffle contract artifact for the proxy contract v1, v2. So here I've added contract because if you just call this proxy, it's actually a reserved variable name. In JavaScript, you cannot use this. Then I define a contract block, and we have a big test should upgrade. So we define a couple of variables here. First, we deploy our proxy. We deploy our v1. We also get a pointer by using web3 for v1 because we are going to send a transaction in a certain way, and it's easier to do it with web3. So same thing with v1, we deploy it, and then we get a pointer with a web3, and then we are going to test the first implementation. So first we are going to upgrade the proxy to v1, and then we are going to call the update var function on v1 and make sure that it works. So the problem is that we cannot call the update var function directly on the proxy using either Web3 or the truffle contract library, because this function does not exist on the proxy contract. So if you try to do this, you're going to have a JavaScript error. So we need to use a low-level call for this. So first, we are going to build a transaction object here with Web3, and we're going to try to call update var with 10. Then we're going to call the encode API function. This is used for low-level call, and it's going to build the data parameter that we're going to use after. Then we are going to estimate the gas for this function call. Then we get the gas price. Then we build a transaction data object, and here we need a few parameters. So the sending address, so that's the admin. Then we send this to the proxy address, very important. We don't send this to v1, we send this to the proxy. Then the data parameters, so that's where we specify which function we want to call on v1. Then for the gas, so we have our gas estimation, but I've also added some extra gas for the code that will run on the proxy. Then the gas price, and then we use a low-level function of Web3 called send transaction, and we pass it the transaction data. And that's how we're gonna trigger the fallback function of our proxy. And after, we need to make sure that it actually worked. So for that, we're going to call a function of v1 but through the proxy. So again, we need to build the parameters for a low-level call. And here, this time, we use web3.is.call with the transaction data. So here we're trying to call var1, a read-only function of v1. And so after, we're going to have the result var1. So this is going to be a hexadecimal number. And so we change it to a JavaScript number with hex to number function. And we make sure this is equal to 10. And we also need to make sure that we still have our implementation address and the admin address in the proxy. We want to make sure that it wasn't overwritten. So this time, we can call directly the implementation function of the proxy. And here we make sure that this is equal to v1 address. And for the address of the admin, this is also the same thing. We do an assertion. And after, we're going to do a similar test, but with v2. So we are going to upgrade to v2. We are going to call a function of v2 and make sure that we can read the new variable introduced by v2, but also we're going to make sure that we still see var1 that exists in both v2 and v1, because even though we have updated the code, the storage of the proxy hasn't changed, so we still have var1. And this leads us to something very important that I wanted to mention. So when you use this method, you need to make sure that you preserve all the state variables that were defined before in exactly the same order. So here, before we had var1, we added var2, and you can add whatever variable you want after this, but you should absolutely keep whatever state variable we had before, otherwise it's going to overwrite all the value we had before, and we don't want this to happen. So this is a limitation of the proxy pattern. You cannot do an update that is completely independent from the previous one. The second method for upgradable smart contract is to use the adapter pattern. So in this pattern, you have a main contract where you have most of your business logic, and some of the functions of the main contract delegate their responsibility to other smart contracts. One example of that is Yearn Finance, the yield optimizer. So in Yearn Finance, you have a function to deposit token, and after your token are invested according to different strategy, and the investment strategy are implemented in this other smart contract, V1, V2, V3. And so at any time, Yearn Finance can add a new investment strategy by deploying a new implementation contract and updating the address in main contract. So it's a little bit similar to the proxy pattern, except that it's a little bit more simple, because in this case, when the user calls a function in main contract, this function actually exists in main contract. It doesn't hit the fallback function of the main contract. When it comes to the business logic of the main contract, you won't be able to change it. However, for the implementation contract v1, v2, v3, you can change whatever you want there as long as it respects a certain interface. Alright, so let's see some code so that you can see something a little bit more practical. So we will go in contract, and here we have our two implementation contract, v1 and v2. So these are very simple contract with a single function, get data, and it return an integer. Same thing for v2, get data, but the implementation here is different, and both of them implement this interface implementation here. So they just need to have a get data function. And here we have our main contract. So when we deploy the contract, we define an admin address, and there is an upgrade function that can be called by the admin, and the admin can change the implementation contract. And when you call the get data function, under the hood, it called the implementation contract, it called the get data function, but depending on which version of the implementation, the return number will be different. Okay, so now let's see how we can test this. So here in the test folder, I wrote some tests. So here we import all our contract, main contract, v1, v2. And first we deploy the main contract. After we deploy v1, we call the upgrade function on main contract for v1. Then we call get data. Then data should be equal 10, and after we're going to upgrade to v2, and so this time the data should be equal to 100. And now we're going to see the last method to make your smart contract upgradable. That's also the most simple method and the one that is the most widely used. So in this method, it's pretty simple. When you want to do an upgrade, you just deploy a new smart contract. It can be completely independent from your first smart contract. And you will also deploy a Migrator smart contract. And you will also deploy a Migrator smart contract to migrate the data from v1 to v2. And this is especially used in the case of tokens. So for example, if you deploy the version 2 of a token as the admin, you'll first deploy your new token, and you will also deploy your Migrator contract, and you will send all the tokens to the Migrator contract. And after, each user is going to claim the new token by interacting with the Migrator contract, and they will be given a v2 token based on their balance of a v1 token. So I'm going to show you this in action with some code. So here we go in the contracts folder, and here we have our v1 token. So very simple, a basic ERC20 token, and then we want to update this to a v2 where we have an extra burn function. And so for that, we are going to use this Migrator function. So here we define a mapping of address to Boolean value where we keep track of the address that already did the migration to avoid doing twice the same migration. Then we're going to have a pointer to the v1 token and the v2 token. Then in the constructor, we are going to instantiate v1 and v2. And then all the holder of the v1 token can call the migrate function. And here we're going to check that the migration was not done already. And here we transfer the v2 token to the sender based on their balance of a v1 token. And actually, I just realized that I forgot to update the mapping here. Okay, so I'm going to reload the page, and yes, here I've fixed my code with this line. Okay, here the migrations contract is completely different from the Migrator. Migrations is a smart contract used by Truffle, so by Truffle internally, so don't be confused. And then we're going to see the test. So we go inside the test folder, we go in upgrade.js, and first we import our various smart contract, the Migrator and the 2 token. And then here we have our test. So first we deploy our v1 token. Then we are going to transfer 100,000 token to 2 addresses. This is just for the test. Then we're going to deploy the v2 token. We also deploy the Migrator contract with the address of the 2 token. Then we're going to transfer all the token of v2 to the Migrator contract. Then we're going to call the migrate function from different addresses. So this one, when we don't specify anything by default, this is going to be from the admin. Then we call this from recipient 1 and recipient 2. And after, we're going to check the various balance of the token. So balance of admin, balance of recipient 1 and recipient 2, and after we assert that these are the proper values. So you notice that in the solidity code of the migrator, we do not burn the V1 token. So this is really up to you. In some cases, it might make sense to burn them. For example, if you're upgrading a LP token. But in other cases, for example, if you're upgrading a governance token and in the new DAO, you cannot vote with the old token, and maybe you don't really care about burning the old tokens. Now, you know 3 ways to make your smart contract upgradable. But there are 2 caveats you need to know. First, when you update a smart contract, it's possible that the new version has some security vulnerability. And we already had some examples of smart contract that was safe, and after an update, a vulnerability was introduced and hackers took advantage of this. The second caveat is that when you make a smart contract upgradable, you break the decentralization promise of the blockchain. Instead of having immutable code, now your users have to worry about what kind of update there will be in the future. One way to reduce this risk and still make a smart contract upgradable is to use a DAO. Instead of having one admin address that controls updates, you have a community that votes for the updates. Upgradable smart contracts is an advanced pattern, and if you want to see other advanced tutorials for smart contracts, you can watch this series on my channel. I will see you there.